Okay, I'll illustrate the idea of complexity by thinking about a chess game. I'm not a chess player. I'm the worst chess player. I gave up chess when I started getting beaten by 3-year-old children. And this is probably a meaningless game right here. But nevertheless, you come and you see the chessboard. I think all the pieces are on the right. I don't think I have two black bishops on the same color. I think it's okay. I think it's a legal position. But you come and you see this chessboard. And you ask, how did it get to be this way? What was the game that actually brought it to this configuration? Or better yet, what's the shortest possible game with the least number of moves that could have brought the chessboard to this configuration, starting with the canonical starting point for a chess game? What are the minimal number of allowed moves that could have gotten us to this configuration? That is called the complexity of the configuration, the minimal number of steps that could have gotten you to this. So it's not a question of how did the chess players actually get here. It's a question of what is the shortest possible game that could have gotten here. That would be called the complexity of the position, the complexity of the chessboard at that instant. It's a computer science question, and complexity is a computer science concept. That's classical complexity. There's a notion of quantum complexity, which is very similar. It doesn't involve chessboards, it involves quantum computers. It involves the running of quantum computers. On the left side, we have some initial configuration of a bunch of qubits. Time evolves. The red lines are called gates, and what are they? They are essentially the same thing as individual chess moves. They have some properties, they're quantum mechanical, but they are chess moves. And as we go from left to right, the game is played. The game is played one step after another. Quantum gates replace chess moves, and eventually you get to a very entangled, complicated state. From an initial state was simple, you get to something complicated. The complexity is a measure of the minimal number of steps that it would have taken, the minimal number of gates that it would take to produce a particular quantum state. But you can say it another way. You can say, given the final output here, what is the shortest way that you could run backward to get to the simple state? You can either think of it as how hard is it to go from the simple, how many steps does it take to go from a simple state to a complicated state, or how many steps does it take if you wanted to work backward from complicated to simple. That's a measure of complexity. And much like entropy, quantum complexity tends to grow. If you start a chessboard in a simple position and you wait a little bit, you expect it to get more complicated, more random, more complex. So complexity, like entropy, is something which tends to grow, but for a vastly longer time than entropy grows. Let's come back to black holes and Einstein-Rosen bridges. Einstein-Rosen bridges grow with time. In fact, according to classical general relativity, they grow forever. Well, let's skip this slide. It's not too important. Yeah, yes it is. Wormholes grow forever. Complexity is something which tends to grow, and in fact, for a large enough quantum circuit, a large enough quantum computer, it will grow for a very, very long time. How long does it take a system to come to thermal equilibrium? That means how long does it take for its entropy to grow to the maximal value? Well, not very long. In particular, if the system happened to be a solar mass black hole, it would take about a millisecond for it to come to thermal equilibrium. How long, thinking of that system as a quantum system, would it take for its complexity to become maximal? The answer is an incredibly large time, e to the 10 to the 78, some incredibly long time. The point is that complexity can continue to grow long, long after the system has come to thermal equilibrium. So what do we know? We know that wormholes grow, and according to classical physics, they grow forever. We know that the complexity of a quantum system grows, if not forever, for an incredibly long time. And the basic hypothesis, which is now being tested, it's still under test. There's not a thing which is infinitely secure, is that the quantum version of wormhole growth is complexity growth. Okay, let's come back to something now. What about quantum teleportation? Isn't that a form of traversability? The whole point of wormholes growing, which is related to complexity growth, is if the wormhole grows fast enough, it cannot be traversed. And that was an important concept because it prevents you from exceeding the speed of light. But what about quantum teleportation? Wasn't that a trick that allowed information to go from one point to another through an entangled system? And if wormholes are nothing but entanglement, doesn't that mean that quantum teleportation can occur through the wormhole? Could it be that quantum teleportation creates traversable wormholes? And the answer is yes. The answer is yes, but at a cost. Remember, I told you that to do quantum teleportation, information in the form of a kind of code book has to be transferred back and forth between the two sides. That information contains no information about what's going through the wormhole or what's going through the quantum teleportation, but it is necessary in order to carry out the protocol. The implication is that you can't do quantum teleportation faster than the time that it would take a signal to go from one side to the other, to go the long way around. We're almost finished. So, let us suppose then that this kind of information can be transported, can be exchanged back and forth between Franklin and Linus. Given that, can Franklin pass through the wormhole and shake Linus's hand? Can wormholes be traversable? And the answer we now know is yes, that the pattern of traversability of wormholes is exactly the same as the pattern of traversability of entangled particles. In fact, not only can Linus or Franklin pass through the wormhole and come and shake Linus's hand, he can also report what he may have seen inside the wormhole, an extra photon or two. And so this back and forth, wormholes can be traversable, but not in a way that violates causality, not in a way that allows you to send information faster than the speed of light. That's the bottom line. But the real bottom line, well, I have a little bit more, but I think it's a little bit too late for this. The real bottom line, I like that picture. What the hell with the picture? The real bottom line is that there is these parallel sets of ideas, one coming from quantum mechanics, one coming from gravity. They seem to parallel each other. They seem to do the same things, and in such a way that one almost has the feeling that gravity and quantum mechanics are almost the same thing, that they are much more deeply related than we ever had any reason to expect. So let's come back to Charlie now. Charlie is sitting and thinking, should he try to quantize gravity? Should he try to use the usual rules of going from a classical system to a quantum mechanical system? And I would say no. I would say no. What we found is not that quantum mechanics and gravity can't fit together. It's they are so closely related that they can't be taken apart. You cannot take them apart. They are just too closely related. Taking them apart and then putting them back together through this process of quantization is the wrong idea. Instead, we should be thinking about how, through the holographic lens, through the holographic connection, quantum mechanics and gravity are almost, or if not exactly, the same thing.